What are the key factors to pay attention to when determining reactivity of a carboxylic acid derivative? Like any other Chem 202 student, you must have come across the reactivity list in the Carey Organic book. Don't want to memorize it? You don't have to. Fear not, a simple Mickey Mouse and a mnemonic or two should help. You'll see what I mean in just a second. Back to Mickey. So if you think of reactivity as the center, or Mickey's head, and the two important factors affecting it as its ears, it looks a bit like Mickey Mouse. Let's start out with the first influence, the ability for the substituent in question to be a good leaving group. What makes a good leaving group? Think about it this way. Try finding the atom that is most stable by itself once it leaves the carboxylic acid. To check yourself, try the conjugate acid test, or CAT for short. The stronger the conjugate acid, the weaker the conjugate base, the more stable the base is by itself. For example, bromine would make a great leaving group. It's highly electronegative and quite stable by itself. Plus, its conjugate acid is a strong acid, HBr. Now let's move on to the other ear. The second factor is the interaction between the substituents and the carbonyl carbon. To understand this rule better, let's take a trip down memory lane and remember electrophilicity. Does that ring a bell? In case it doesn't, an electrophile is something that attracts electrons, so it has a partial positive charge to it. Remember, the stronger the electrophile, the more likely the molecule will react in order to get those electrons. To see how differing strengths of electrophiles impact reactivity, let's look at an example. Let's compare acyl chloride, acetic anhydride, and isobutyric acid. In acyl chloride, chlorine is very electronegative. This means chlorine will generally tend to draw the negative charge towards itself and therefore away from the carbon. The more electronegative the atom near the central carbonyl carbon, the more it will pull the negative charge towards itself, starving the carbon of electron density. This will make carbon very electrophilic and quite susceptible to nucleophilic attack. Next, we have acetic anhydride. Notice how carbon is attached to two electronegative oxygens. On first glance, this looks even more susceptible to nucleophilic attack, since oxygen is generally more electronegative than chlorine. However, this molecule can resonate, meaning it can delocalize the negative charge and spread out the electron density. This means the carbon won't be as electrophilic. Plus, keep in mind that carbon and oxygen are more similar in size and electronegativity, and they are in the same row of the periodic table, so they will have better orbital overlap. Finally, the isobutyric acid. The structure looks similar to acyl chloride, but instead of highly electronegative chlorines, there are only not as electronegative carbons. Since there's not as strong of a pull on electrons, carbon can retain some of that electron density, making it not very electrophilic at all. This will be the least reactive of them all. Take care.